the most common and simple form of shunt regulator is Zener shunt regulator. In this topology, Zener diode is placed in parallel to the load and hence the name Zener shunt regulator. I am Reshma and today we will look into Zener shunt regulator in detail. Today we will talk about Zener as shunt regulator, calculation of current in Zener and load, power consumption of various elements. In our previous videos, we saw that a Zener diode maintains its breakdown voltage across it when it is in reverse biased condition. Now, let us connect a load across this reverse biased Zener diode. In order to obtain our output of 5 volt, we need a Zener diode with a breakdown voltage of 5 volt. Let us consider the following circuit shown with 15 volt supply. Let the series resistor be 1 kilo ohm and the load resistor be 1K. The corresponding currents are I1 flowing through R1, IZ flowing through the Zener, and IL flowing through the load. For simplicity, let us assume that the Zener diode is not present in the circuit. Now, the circuit is similar to that of a voltage divider circuit. The output is given as 7.5 volt for the given corresponding resistors. This voltage of 7.5 volt is greater than the Zener breakdown voltage of 5 volt. Therefore, if a Zener were present as shown in the figure, then it will maintain its reverse breakdown voltage. In this case, it is 5 volt. I1, which is the current flowing in the resistor R1, will be split into IZ and IL. Let us now calculate the current in the circuit. With a breakdown voltage of 5 volt, we know that the Zener will maintain 5 volts across it. Since load resistor is in parallel to this Zener, this means that the output voltage is 5 volt for the circuit. The current IL can be calculated as V out by R2, that is equal to 5 milliamps. Now the voltage across R1 will be V in minus V out, that is equal to 15 minus 5 volt, that gives us 10 volt. Then the current flowing through R1 will be V1 by I1, that is equal to 10 milliamps. Since the current I1 is split into IZ and IL, we can calculate IZ as 10 milliamps minus 5 milliamps, that gives us 5 milliamps. We know the voltage and current flowing in the components used. Now, we can find the power loss in the components. Power loss in R1 resistor is given as V1 into I1, that is equal to 0.1 watt. Power loss in the load resistor is V out into IL, that is equal to 0.025 watt. Power loss in the Zener is given as Vz into Iz, that is equal to 0.025 watts. The total power taken from the input will be the sum of the power dissipated in the components used. It is P1 plus PL plus PZ. The total power loss is given as 0.15 watt. This power loss can also be calculated as Vin into I1, that is equal to 0.15 watt. We can observe here that the power loss in R1 resistor is twice the power loss in the Zener and the load resistor. Let us reduce the load resistor to 500 ohms. For simplicity, let us assume that the Zener diode is not present in the circuit. Now the circuit is similar to that of a voltage divider circuit. The output for this circuit is given as 5 volt. This voltage is exactly equal to the Zener breakdown voltage of 5 volt. If we use the Zener as shown, then in this case the Zener will not break down. However, it is ready to break if the voltage goes beyond 5 volts. Current in R1 will flow into the load resistor and there is no Zener current. Let us now calculate the current in the circuit. Output voltage is 5 volts. Hence, the load current can be calculated as V out by R2, that is equal to 10 milliamps. Now the voltage across R1 is given as Vin minus Vout, that is equal to 10 volt. Then the current flowing through R1 will be V1 by I1, that is equal to 10 milliamps. Since the current I1 is split into IZ and IL, we can calculate IZ. IZ is given as 10 milliamps minus 10 milliamps, that is equal to 0 milliamps. We know the voltage and current flowing in the components used. Now we can find the power loss in the components. Power loss in R1 is given as V1 into I1, that is equal to 0.1 watt. Power loss in load resistor is given as Vout into IL, that is equal to 0.05 watt. Power loss in Zener is given as Vz into Iz, that is equal to 0 watt. The total power taken from the input will be the sum of the power dissipated in the components used. It is nothing but P1 plus PL plus PZ. Hence, the total power loss is 0.15 watt. This power can also be calculated as Vin into I1, that is equal to 0.15 watt. We can observe here that the power loss in R1 is twice the power loss in Zener and load resistor. It can be further noted that the power taken from input remains constant even when the load changes. Let us reduce the load to 100 ohms. For simplicity, let us assume that the Zener is not present in the circuit. Now the circuit is similar to that of a voltage divider circuit. With this resistors, we get an output voltage of 1.36 volt. This voltage is lesser than the Zener breakdown voltage of 5 volt. If we use a Zener as shown, then in this case the Zener will not break down. Current in R1 will flow into the load resistor and there is no Zener current. From the above experiments, we can observe that for calculating Zener breakdown voltage, we need to assume that the Zener is not present in the circuit, calculate the voltage across the load for the given circuit conditions. If the voltage is greater than the Zener breakdown voltage, then it will break and it will maintain the output voltage. If the Zener voltage is lesser than the breakdown voltage, then it will not break and it will not be able to maintain the output voltage. In this video, we saw how a Zener diode operates as a shunt regulator. We also learned the method used to calculate the Zener breakdown voltage. We will learn more in our subsequent videos. Till then, keep exploring and learning. Thank you.